Thank you, Professor Roland, for this very lovely introduction. So I hope that everyone is fine this morning. Have a very pleasant morning to everyone. And we had a small confusion because outside it was announced at 10:50, but now we stopped 10 minutes later. But I think that's okay. So thanks so much for this very kind introduction. Today I would like to talk about healthy food production, how to avoid transfer of toxic metals from paddy soils to plants. And when we're talking about paddy soils, then we need to be aware that rice paddy soils are important producers of rice, and rice serves as a staple food, as you know, from many countries across the world, in Asia, but also not only in Asia. And when we're talking about rice paddy soils, then we need to be aware that redox processes are very important because they are driven by the water regime. We have oxic conditions, anoxic conditions in case of flooding. That means those paddy soils are often highly polluted with toxic elements. Arsenic is a big issue, but also cadmium, mercury, but also antimony, selenium, and many other elements. So I choose today for you a few elements to demonstrate to you the problem. So when we have those contaminated paddy fields, then there is a mobilization and transfer into the groundwater as well as in plants. It's possible, and then we have a potential transfer into the fat chain. And of course, this is a potential risk, especially if you consume everyday rice, and if the rice is contaminated with mercury or with arsenic or with cadmium. In China, cadmium is a big problem, but also arsenic, and in certain areas, mercury. So that means we need appropriate remediation technologies, and one option is that amendments are frequently used to immobilize toxic elements, and one option is that biochar is used as a remediation option. And I have one example for you based on this province, Guizhou province. Two postdocs of mine are working there, and this is a Washan mercury mine. This is known as the mercury capital of China. A lot of high concentrations of mercury are detected there, up to 800 milligram per kilogram, and the critical limit here is 1.5 milligram according to the Chinese standards. The German standard is 2 ppm. So we have high concentrations of mercury, and you can see the mining site here, mercury tailings, mercury polluted soil. So mercury is really a big issue in this province, and two postdocs of mine, originally from Guiyang, are currently at my lab, and they conducted a field experiment where they applied this biochar to the paddy field, as you can see here. And under flooding conditions, you can see here, we have the control soil, and here's a biochar treated soil, so we can have different treatments, and we have different water regime, and of course the water regime determine largely the redox processes. So when we have a look at the total mercury concentrations on different plant species, then we can see the total mercury. Here's the rice, so there's no big difference. But if you compare the methyl mercury, then we can see that the rice contain a lot of methyl mercury, especially in comparison to many other plants. That means the highly toxic methyl mercury can be more accumulated in rice crops, than in other crops. And if we have a look particularly in rice, then we have to be aware that about 84% of the toxic mercury, methyl mercury, is accumulated here in the rice grain, and to a less amount in stem, leaves, and roots. That means most methylated mercury is sequestered in the rice grain. And this is, of course, highly toxic, and this is a big problem. And here are some results of the field experiment, and one you can see on the left-hand side. Here you can see the concentrations of methyl mercury content in the paddy soil. The dark color is a control soil, and here's treated with biochar. After 60 days, there's no big difference, but after 90 days of after the field experiment, you can see a difference. That means that biochar treated soil has less methyl mercury, and after 120 days the effect is even more obvious. And if we have a look on the methyl mercury concentration in the rice, then you can see this effect is very obvious between the control soil and the biochar treated soil. That means, in other words, the application of biochar to the soil can decrease the methyl mercury content in the rice to a significant amount. So this is one story what I would like to present to you, and now I would like to go from the field experiment to the lab, because we aim to elucidate the redox-driven processes. What we are doing here is we have a very special technique, the so-called biogeochemical microcosm technique, what you can see here, and what we're doing in the laboratory, we simulate a flooding of the soil. We take the soil, bring it to the laboratory, and flood it, and then we create here a slurry, stir this continuously, and then we are able to monitor the temperature, the pH, and the redox potential. These are electrodes, and those electrodes are connected with a data logger, and those data loggers connected with a computer, and we are able to monitor those three parameters in a very high temporal resolution. That means every 5 minutes those data will be recorded, and this enables us to study the kinetics of those parameters. At the same time, we are able to add oxygen or nitrogen. When we add oxygen to the system, then we increase the redox potential. If we add nitrogen, then we decrease the redox potential. This means we are able to conduct experiments to systematically control the redox potential. And this is how the experimental setup looks in reality. So this is a microcosm system. The blue line is oxygen tube, the black line is a nitrogen tube, and all this is airtight here. And on the other hand, this is a control unit. Here we measure the airflow. Here we can add acid and base. And here is a display, so we have a real-time measurement here of redox potential, pH, and temperature, what you can see here. So that means this technique enables us to conduct systematically experiments, not just do flooding, anoxic, and drying oxic. We can do it in very pre-definite steps. And all these techniques is published in those papers, what you can see here. I have 16 of those units in my laboratory as well available. This is the reason why many scientists all over the world come to my lab to conduct those experiments there. So the next story is a little bit about arsenic. Basically, in the soil-water interface, we find arsenic 3 and arsenic 5. What you can see here, arsenic 5 can be reduced to arsenic 3, arsenic 3 can be oxidized to arsenic 5, and both happens in the soil as well as in the water, and of course we have a lot of interactions between the soil-water interface. There are some other arsenic compounds such as arsenobetaine, arsenocholene, arsenosugars, arsenolipides, which are also involved in those processes. And then you have here the arsenic 3, and this toxic arsenic 3 can further methylate it through microorganisms or fungi to the highly toxic monomethyl arsenic. And this is highly toxic. Of course, this process is reversible, but this monomethyl arsenic can further methylate it through fungi and microorganisms to the highly toxic dimethyl arsenic. And then we conducted such an experiment. And this is what I would like to demonstrate to you here. Here you can see the redox potential, minus 400, plus 600, the same here. Here you can find the monomethyl arsenic, here the dimethyl arsenic. And what you can see is that under anoxic conditions, we have a high production of both toxic arsenic forms, monomethyl arsenic, as well as dimethyl arsenic. And we're also using the XANES spectroscopy, the so-called fingerprinting, the X-ray absorption near edge structure to determine the specific speciation of arsenic, and you do also mapping, the micro XRF mapping, as you can see here. Then we are able to detect differences and allocations of arsenic, chromium, iron, and many other different elements. This example demonstrates to you another story. This was happened in the coastal area of the Delaware Delaware area in the United States. Here you can see the seawater, here you can see the river water, and here are the different standards. The arsenic sulfur compound, here is arsenic 3, and here is arsenic 5. And here you can see the different status of redox from anoxic to oxic, here also from anoxic to oxic. And what you can see is, when we move from anoxic to oxic, we also have a shift from arsenic sulfur compounds to arsenic 3 to arsenic 5. And this is very obvious when you have a look here on the percentage. Here you can see anoxic conditions, oxic conditions. That means if you increase the redox potential, the arsenic sulfur compounds decrease, but at the same time the arsenic 5 content increase and arsenic 3 content decrease. And we published this last year in ES&T. Another story, what I would like to demonstrate to you is a soil from Korea, because now we are in Korea, so I also would like to present some results from the Korean soil. Together with Professor Jorg, we had this experiment. It's a soil which is highly contaminated in arsenic and lead. As you can see, it's high contaminated, slightly acid. And we used the untreated soil, and we treated the soil with pine saw biomass, and with pine saw biomass biochar produced at 300 degrees and produced at 550 degrees. And you can see the different amendments here. And you can see also different scanning electron microscope pictures here, and you can observe the differences in the structure of the biochars. And here you find also some properties. That means also, basically, it's very important that we increase the pH when you increase the temperature, but that's very well known, but it's important for our story now. So this is an example from this experiment from the Korean soil. Here you can see the control soil. Here's the soil plus biomass. Here's the soil plus biomass produced at 300 degrees. Soil produced as biochar produced as 550 degrees. On the left-hand side, you can find the redox potential, plus 400 to minus 400. Here you can see the incubation time, and on the right-hand side, you can see the pH. And this line represents the average of 4 replications each, and these are the real-time measurements. That means this line represents data, about 44,000 data. That means those results are really very reliable. And now you can really observe, here we flooded the soil, oxic conditions, and here we have anoxic conditions, and now we are able to increase the redox potential stepwise, in steps of 100 millivolt, from minus 300, minus 200, minus 100, and so on, and to conduct different redox cycles. And at the same time, we monitor the pH, and what you can see here, the pH is very stable, but decrease when we increase the redox potential. This is a very well-known behavior. If you have oxic conditions, pH is going down, but has also certain effects on the mobilization of different trace elements. Important to realize that the pH here increase in the soil treated with biochar produced at 550 degrees. So now let's have a look on the results. Here's the control soil, biomass, biochar 300, biochar 550. And what you can see, here's the phytoavailability of arsenic. That means the plant availability of arsenic. And our expectation was that, or our aim was, that we decrease the mobility, the phytoavailability of arsenic using the different amendments. But as you can see, the difference is not that big. Quite an opposite. Here you have even a mobilization of arsenic when we use the different amendments, the different biochars. That means what is in terms of the phytoavailability of arsenic, the treatments with biochar in this specific case does not work so well. But on one hand, what is not good for arsenic is good for lead. Let's have a look on the phytoavailability of lead, and then you can see here, especially in the soil treated here with biochar 550 degree, that there's a decrease under oxic conditions of the phytoavailability of lead. That means here it works very well. The biochar produced at 550 degrees has a certain effect to decrease the phytoavailability of lead. That means what is good for lead is not good for arsenic. So this has something to do with the chemistry, because the biogeochemistry is contradictory of those two elements. That means if you have a multi-contaminated soil, things becoming very complex in those dynamic systems. Because those systems, when they are flooded, when they are dry, you have very dynamic processes, and those processes have a certain impact on the mobilization of different trace elements. That means the mobility of arsenic increased under reducing conditions. Under oxic conditions, we have a higher amount of available arsenic, and the pine salt biomass reduced the mobility of and phytoavailability of arsenic, and the biochar produced at 550 degrees reduced the phytoavailability of lead. The technique, the biogeochemical microcosm system, allows us to study mechanistically pollution control processes in soils and sediments, and it allows us also to study the kinetics and the dynamics of many trace elements and further harmful substances. I showed that to you on the example of mercury, of arsenic, as well as on lead. That means similar studies should be conducted with a variety of biochars and paddy soils around the world, and we also believe that we should have a look further on the different species of trace elements in those wetland soils under dynamic redox conditions. This is a very emerging field, and of course we also should verify our results which we gained in the laboratory under field conditions, also with view to an adequate remediation option, aiming to minimize the potential risks to humans and to the environment. That means the take-home message is: be carefully with the selection of amendments. Biochar is not as biochar. We all know it largely depends on the properties, on the feedstock, on the temperature, and what is good for one element is not good for another element. That means the selection of amendments or biochar to soil contaminated with different trace elements should be made carefully, especially when you have dynamic redox conditions. And here are some papers just from this year here about pine salt biomass and different biochars, and here the effect of biochar on different trace elements. And here about the mobility of arsenic and lead, and here a paper about biochar where it works very well. This type of biochar had a very good effect in terms of the stabilization of the different trace elements. And here's some reviews which I would like to recommend for you. Just released as an important review about wood-based biochar for the removal of potential toxic elements in water and in wastewater. Here a critical review in International Material Reviews. Here a review about the interaction of arsenic with biochar in soil and water. And here a review about trace elements in the soil-plant interface, phytoavailability, translocation, and phytoremediation, a review published in Earth Science. And here a review about the cycling of mercury in the environment, published in Critical Reviews in Environmental Science and Technology. And a little bit promotion, just released my new book about nickel in soils and plants. So it's just last week. It's available in Amazon and everywhere. You can order it for your library or for the students whenever you like. And last year published my book about trace elements in soils and sediments, I would like to recommend this for you for your further reading. And now I would like to thanks for your attention, and I'm ready to take your questions. Thanks very much. Nancy, or shall I? Okay. Are there any questions? I thought then Nancy will guide, but no. Okay. Are there any questions? Not the case? Okay, then I would like to